Welcome to Chapter 14, Part 1. We're going to talk about infrared spectroscopy and mass spectrometry in this chapter. This is the first lecture for Unit 1, and this is the style of lecture you will be receiving. On the left, you have the PowerPoints. These are available to you on eCampus. I definitely recommend using them while you're studying, or maybe printing them out and taking notes on them. I have a whiteboard over on the right side of the screen. I do like to use the whiteboard a lot in my face-to-face lectures. And so this is as close to my teaching style as I can get while we're here on this blended or online type of structure. I do recommend that you take notes while I'm lecturing, because taking notes is part of starting to commit things to your memory. I also recommend watching my lectures. I will go into more depth than the slides do. I will also let you know when we're skipping over something. I will work problems. You are responsible for the material in these lectures. Okay, so let's jump on in. We are going to be covering in this unit 3 different types of instrumentation and experimentation that falls under the heading of spectroscopy and spectrometry. We're going to be covering IR, we're going to be covering mass spec, that's chapter 14, and then we're going to hit NMR, nuclear magnetic resonance, in chapter 15. As an organic chemist, we do a lot of setting up of reactions, functional group transformations. We will get back to nomenclature and reaction mechanisms and synthesis once we complete Unit 1. But this unit is all about characterization. All right, you may have some experience with IR from Organic 1 lab. Whenever you spend time making a new compound and purifying it, you have to have evidence that you have what you say you have. Or you have to have ways of identifying unknowns, whether they're unknown natural products or unknown byproducts in a reaction. IR and NMR and mass spec are really powerful tools. Spectroscopy, the word spectroscopy, means the study of how matter interacts with light, right? And not just visible light, any electromagnetic radiation, right? So anything on that spectrum. We're going to be looking at how matter interacts with light and what we can take away from those interactions. To do that, we're going to review a little bit. So when you first were introduced to electromagnetic radiation in general chemistry, all right, or light, you were taught about the duality of light, right? It could be thought of as a wave, and sometimes that makes the most sense when describing phenomena. And sometimes it can be treated as a particle, right, or photon. And that can be really useful in describing phenomena surrounding light. We're going to see the same thing when we talk about matter. There are some definitions, right, that come up as we're talking about spectroscopy. When you study light, there are characteristics like wavelength, right, and that's measuring peak to peak. That's inversely proportional to energy, right? The longer the wavelength, the lower the energy. Frequency, because all light is moving at the speed of light, right? So it's moving at the same speed. The longer the wavelength is, the less waves will pass through a point in a given period of time. All right, so frequency is inversely related to wavelength, which makes it directly proportional to energy. High frequency equals high energy. This should be a very familiar picture. pretty much, I think I recall seeing it in junior high science classes the first time. But this is your whole electromagnetic spectrum from your high energy, high frequency, short wavelength, cosmic and gamma rays, all the way down to your long wave, low energy, low frequency radio waves, with visible, somewhere here in the middle. We're going to be really interested in infrared for IR spectroscopy and radio waves for NMR. Now, I want us to think about the visible spectrum for a minute. So to understand how infrared spectroscopy works, it can be really useful to think about a spectroscopy that you learned about in general chemistry. Right? This isn't your first time hearing about spectroscopy. So we're going to take a little bit of a look at this continuous spectrum. Right? When you take a flashlight with a white light bulb or light from the sun, if you can direct that light through a prism, right, it diffracts those different wavelengths and separates them out so that you now can see the rainbow. You can see all of the colors of the visible spectrum, right? And that there's no breaks. It's just a continuous fade from purple down or violet down to red. There's some important experiments that started to help us get into a discussion of quantum mechanics when we looked at this experiment with H2 gas. So if you take usually it's a glass tube with an element. So in this case, it's H2. And you apply energy. Let's say that we're going to use electricity. All of that hydrogen is going to get excited, and as it relaxes, it emits light, right? That tube is going to glow. Now, if you put that light through a prism, right, and separate out all the different wavelengths, you're going to get an emission spectrum, right? And an emission spectrum for hydrogen looks like this. It's not continuous. You don't see all the colors of the rainbow. In fact, you only see 4 very specific lines here. So that's an interesting thing about the light that comes from electrified H2 gas. Let's think about one other experiment here. If you take that same tube of gas and instead of electrifying it, let's say you shine white light, so it has all of the colors of the rainbow through. So you're just shining that light through this hydrogen, this glass tube of hydrogen. The light that comes out the other side, if we go ahead and we shine it through a prism so we can analyze it, you're going to get an absorption spectrum. Right? This guy right here. Almost all of the white light passes through, but you have some black bands. Now, the reason why there are more lines on this one than the previous is just because we're going a little bit further into the UV side. It's nothing to worry about. What is important to recognize is that these black bars line up with the spectral lines you see in the emission spectrum. And the duality of nature, that wave/particle duality, is also going to be applied to matter, right? Why did we see those spectral lines? If we take an electron, right? And so we're gonna indicate an electron with that little arrow. And we say that where it is, before you add electricity, before you shine light through it, is at ground state, and we're just going to say that's at level 1. As it turns out, the amount of energy that electron can absorb is not infinite. There are certain levels, allowed energy states, that electron can occupy. So there might be an n equals 2 or 3 or 4. Right? And so this little electron can only absorb energy that bridges one of these gaps, right? So there's only certain photons of light that have enough energy, right? And that would be absorbed in an absorption spectrum that would get us from n equals 1 to n equals 2 or 3 or 4. This can also help us to understand the emission spectrum. We're exciting those electrons, say we have one excited up to 4, with electricity instead of light. Well, even an excited electron isn't going to stay excited. It's going to relax, and it gives off that energy in a little packet or photon of light. And so it only gives off packets of light, these guys over here, that correlate, right, to specific energy drops, right? It's only going to give off packets of light that cover one of those allowed gaps. Okay, so this is one way that matter interacts with light. Electrons, which are matter, are excited by photons of visible light. And we see that it's quantized, right? There's only allowed states. This is going to be important for helping us to understand what's going on with IR. So let's switch over and talk about that. We are going to be covering NMR in the next chapter. It uses radio waves. It gets its own whole chapter because it's a little bit more complicated, and it allows us to specify arrangement of carbon and hydrogen. It's very powerful for organic. IR, which we're covering here, uses infrared radiation and is helpful for figuring out functional groups. UV vis is another type of spectroscopy we're not going to cover in this class, but there is a small section, I believe in chapter 16 on it, and it tells you about conjugated systems. Okay, so on the macroscopic scale, when you're looking at matter, we tend to think of it as exhibiting continuous behavior, right? If you have a tire and you apply some energy to make it rotate, you can make it go any speed, from 0 to whatever your max is, and just like anything in between. But on the molecular level, we're going to see quantum behaviors. It would be as though your tire could either stand still, it could go 5 miles an hour, or it could go 20 miles an hour, and that's it, nothing in between. So we're going to see the fact that matter exhibits these quantum behaviors is really helpful and allows us to study structure through spectroscopy. For instance, when we think about how does infrared radiation affect matter? Does it excite an electron? No, that's the visible spectrum. We are going to be affecting bonds, right? We're going to cause them to vibrate, to bend, to stretch, right? And different bonds, right, whether it's a carbon-carbon bond, a carbon-hydrogen, a carbon-oxygen, single, double, triple, what kind of bond will only have certain vibrational or stretching states. So it will only absorb certain wavelengths of infrared radiation. It will then eventually release that radiation as heat. Right? IR is what we experience as heat. These are just some of the ways that the bonds can be affected, right? You have this sort of lengthwise stretching. You have this bending vibration where they're moving in towards one another. And you have this twisting vibration where they're one's twisting towards us, the other's twisting away. We are mostly going to be looking at stretching frequencies. That's not terribly important right now. Many of the experiments that we learn here have other applications, and IR is no different. We see 2 applications of IR spectroscopy when we look at night vision goggles and some cancer screenings. So the light from the sun has infrared, visible, and UV light in it. The UV is what can burn us, the visible is the light we see, and the IR is what we experience as heat. So over the day, these trees and this house, the windows, the chimney, the roof, all are absorbing that infrared radiation all day. And then as night comes and all of the bonds and all of that material start to relax, start to emit infrared radiation. And so a night vision goggle can detect that IR and create a contrast map between things that are more or less hot. For this picture on the right side of the PowerPoint, what you're seeing is breast cancer. And what's interesting about cancerous tissue or tumors is that they have their own vasculature that's often more chaotic than healthy vasculature. So what they're doing is they're cooling the body, and everything with normal vasculature cools down, and then the cancerous tissue does not cool down at the same rate, and it creates kind of like this hot spot so that you can visualize where the tumor tissue or the cancerous tissue is located. So lots of interesting applications for IR. We're going to focus on identifying functional groups and then later pairing it with other spectroscopies. So this should look somewhat familiar to you, right? Especially after we just talked about excited and ground state electrons. The CH bond and the CO bond are just arbitrarily chosen here. They're different bonds, and so they're going to react or interact with light differently. The CH bond has quantized energy levels or allowed vibrational states, just like our electrons did. And these gaps, these delta E's, will correlate to a specific photon of infrared radiation. All right, different bonds are going to have different allowed states, different sized gaps, and we use that to our advantage to identify what kind of bonds are present. The spectrometer itself irradiates your sample. It's a pretty easy setup. You have a sample that's prepared in some way, and you shine IR wavelengths through that sample, and then you catch it in a detector, right, to see which wavelengths were absorbed, which ones were transmitted. Now, if you've been at Blinn, our IR setup is so easy. You can put a solid or a liquid directly onto the instrument and cover it with a little probe and run your experiment. These notes right here are just alternate ways of preparing samples. Liquid samples are often smushed between salt plates, and solid materials may often be mixed with KBR and tightened into or compressed into a pellet that you can shine light through. The reason sodium chloride and KBR are used is it's an ionic bond, right? And that type of bond is not going to absorb IR in any of the same places as the covalent bonds that we're studying. So there's different instruments where the setup of the experiment might look a little different, but overall, you prepare it in some way, shine IR through it, detect what comes out the other side. The IR spectrum itself typically has percent transmittance on the y-axis, and then wave number, which is related to wavelength, on the x-axis. And something that is transmitted completely means it wasn't absorbed. So it's these signals that come down that show that not everything at this wave number was transmitted. That means it was absorbed, and then we can relate that to a specific bond. In the next video, we will talk about how to read an IR and what signals you should work on memorizing.